And welcome to this IB Explainer video on electric fields. We're going to look at some definitions and then hopefully a couple of calculation examples which should help you further understand electric fields. As ever, please do not hesitate to ask questions if you have them. When we tend to think of electric fields, we tend to look at pictures like the one you can see on the left-hand side of the screen. On the top, we've got a positive charge with lines pointing radially outwards. And on the bottom, we've got a negative charge with lines pointing radially inwards. Let's think a little bit more of those. We'll try firstly to define what an electric field is. You should be aware is that electric forces exist between electric charges. It's a non-contact force, and this means that when I place a charge near to another charge, they will both experience an electrostatic force. There's therefore an area surrounding all charges where another charge would experience a force. And that is the electric field. Put simply, the electric field is a region of space in which a charge will experience an electrostatic force. Now, when we want to draw electric fields, we represent them using field lines. And those field lines are drawn in a very specific way. When we're drawing field lines, we imagine we're placing a small positive test charge near to our source charge. So for example, we might imagine we're placing a small positive test charge just above my blue positive charge here. Well, we then think, what would the direction be on the test charge due to the source charge? Well, the test charge, as it is positive, would be repelled by the source charge and therefore pushed away, and therefore upwards. This would happen at every position around the source charge. So our electric field lines are used to show the direction of a force on a positive test charge placed at that point. And you can see that further in the bottom example. If I placed a positive test charge around my negative source charge, at all points the two would be attracted together, and so therefore the test charge would be pulled towards the source charge. And that's why the lines have different directions. What's similar about them, however, is that they're all radial. And what that means is that they're pointing out from the center of our source charge. What does that mean? Well, it's not just a nice way of visualizing, it's actually a really powerful mathematical tool. The fact that these lines diverge or push apart from one another represents the fact that the field strength is changing. When we're drawing fields, the closer together the field lines, the stronger the field. So what you should be able to see is that in both of our source charges, we have got a strong field close to the source charge and a weak field further away, because those lines are getting further apart the further away we go from the charge. This ties in with our definition of electric field strength, which is very similar to gravitational field strength. So I'll just put it up. The electric field strength, E, firstly it's a vector quantity. Okay, we'll talk about that in a second. And it's defined as the electrical or electrostatic force per unit positive charge placed at that point in the field. Okay, let's have a think about what that means. Firstly, we know that the electric force is calculated according to Coulomb's law by K times Q over R squared. Here, capital Q is my source charge and small q is my test charge. What we're saying here is that the electric field strength is the force per unit charge, and in particular, force per unit positive charge. This is exactly the same as when we say G is the gravitational force per unit mass. The only difference is that we have to specify positive charge as opposed to simply charge. And the reason for that is because positive and negative charges will experience a different direction of force. So every time we are writing the definition of electric field strength, we must include the fact that the unit or the test charge is positive. We cannot write charge simply on its own. If we then go back to our equations, we can combine the two. We're going to substitute the second equation here into the first. Okay, looks a bit messy just now, but you should hopefully be able to see that the two small q's are going to cancel. And therefore we're left with an answer which says electric field strength is equal to kq over r squared. And again, this is very similar to our gravitational field strength equation. Instead of mass, we're thinking about charge, and instead of big capital G, we're thinking about k, the Coulomb constant. Notice one small thing. We have not specified anything about the charge on the source charge. Source charge can be positive, or the source charge could be negative. Therefore, as we'll see in the following example, the electric field strength itself could be positive or negative, and that's because it's a vector quantity. We'll come on to that in a second. Let's look at these two examples. We want to calculate electric field strengths, and we're going to assume that we're using point charges, and therefore we can use our equation E equal to kq over r squared. Okay, here k is simply 1 over 4 pi times epsilon naught. I use the k variation in this case. However, you're equally okay to use the 1 over 4 pi epsilon naught. So we can use our equation. In the first case, our capital Q, our source charge, is 10 microcoulombs. So that's 10 times 10 to the minus 6. And we're at a distance 1.5 times 10 to the minus 2 meters. Be careful whenever we're checking units. Okay. Now what I've deliberately done in this case is I've included the fact that this charge is positive. And I like to do that just to remind myself, because it's often something that can get lost. When you're dealing with charges, I do recommend you always explicitly state positive or negative. And as you know from your work with Coulomb's law, that can be very helpful in determining the sign of the force, or in this case, the electric field strength. Now here, we work out, we've got an electric field strength of 4 times 10 to the 8 newtons per coulomb, force per charge. And if I was being really, really pedantic here, then what I would also add at the front here is a plus sign to show that my electric field strength is positive. We'll do the same for the next one. Again, we can use the same equation, kq over r squared. But this time, we have the same k, but we have a different q, minus 0.85 times 10 to the minus 3. We're then left with an answer which is minus 1.2 times 10 to the 6. Now what does this mean? When we have a positive value of the electric field strength, that means that my positive charge would be pushed away from the source charge. If I have a negative value of the electric field strength, then that means my positive test charge would be pulled towards the test charge. So there's a lot of value in leaving those positive or negative signs, because it tells you a lot about the effect of that field on any test charges placed inside it. And that's going to be very important when we think about the ideas of electric potential. That's all for today's video. I hope that was helpful. Please do let me know if there's anything you're not sure of, and I'll be happy to get back in touch with you. Thanks for watching.